Hello, my name is Christian Boyne. I am a student under Physics 205. This is Experiment 5. We're working with an electric motor and we're going to build one today. Today is July 24th, 2017. So some background information on how an electric motor works. Electromotive force is equal to the negative change in rate of magnetic flux. So magnetic flux is the magnetic field times the area of the object under consideration. If you make a coil of wire by scrunching up coiled insulated copper wire, you can have a constant area. If you hook up an electromotive force across the coil of wire from this end to this end, that means you're going to have a constant electromotive force. Something is going to have to then change to compensate, and it will produce a torque in the current loop that causes it to rotate. So I'm going to demonstrate these principles, and the current in the loop, we can calculate the frequency of the motor by this equation. This equation is derived from the equation epsilon equals negative d theta b over dt. When there is current moving in a loop, you can determine the direction of the area vector of the loop by curling your fingers in the direction of the current. Your thumb then points towards the magnetic dipole moment. The direction in which the loop is going to rotate is going to be so that the area vector, as seen here, is going to try to point in the direction of the magnetic field. And we're going to see this principle in action. Now I'm going to start assembling the motor itself. Materials used in this experiment are a GoLink sensor connected to the Vernier magnetic field sensor that is connected to my computer. That'll allow me to sense the magnetic field's magnitude at the height in which the current loop is going to be placed. So this is going to be what makes up the current loop. This is enameled copper wire. It's 1.5 meters long. You can roll it around a circular object of a known diameter or measure the diameter yourself after. After you've curled it up and got it into a very compact solenoid-like shape, you are going to then loop the wire through and around to tighten up the coil and place it through these two clips. These clips have pieces of paper clip crimped around it so that the wire can rest in the little loops here, and then that will allow it to maintain contact with the voltage difference across. The voltage difference is made by connecting alligator clips to the clips themselves and then to the negative and positives of the battery. I will also be hooking up a switch in series. So by knowing the height at which the current loop is going to be placed, I will use the magnetic field sensor to determine the value for B. When the current loop has been assembled and placed within the clips, it needs to be placed so that the uninsulated portions of the wire are in contact with the metal. The alligator clips will then be connected to the switch, and from the switch they will be connected to the battery, and then you take an alligator clip connecting it to the positive and to this side of the loop, close the switch with the magnet in place, and we should have a working motor. Sensor near the center of the loop, we can obtain a value of approximately 1.5 milliteslas. So knowing that, we can then plug in the known voltage, which is 3 volts, the magnetic field, which is 1.5 milliteslas, the area, which is a 7 centimeter diameter loop, and then the number of coils, multiply that by 2 pi in the denominator, and we can figure out the frequency of the motor. When you have current moving through a loop, you are going to be producing a torque on that loop if it's subject to a magnetic field. This permanent magnet here is going to supply we're going to call it an ideal uniform magnetic field permeating up and through this loop. Right now, in this position, the magnetic field would be through the center of the loop, and the angle between the magnetic field and area vector would be effectively 0. In this condition, the torque is maximized. So when this goes through rotation, the area vector differs from the magnetic field, and the magnetic dipole is going to do work to try to restore it back to its original state. So in the case of this setup, when I close this switch and give it a slight twist, the magnetic field is going to try to keep it restored at that position. But if I flick it hard enough, we should see it go into a state of motion. So it's now spinning. You just have to give it a flick to get it to start to rotate, and the connection is not very ideal as some of the enameled part of the copper wire is still on there, but right now we do have a connection. So there's current flowing completely through the whole circuit, and it's the torques in the current loop that are allowing this to rotate. If you do the reverse of this situation and rotate a current loop in a magnetic field, you can actually produce a potential difference, and that is how generators work. So, concluding the experiment, we've really just done a real-life representation of Faraday's law and how electromotive force is equal to the negative time rate of change of magnetic flux. In a case of a motor, we have the electromotive force across the motor producing a current in the loop, which creates a magnetic dipole and thus a torque.